I thought it would be good to review what we went over in class about MeterEffect and tolerancing. I've created 2 videos already and posted them on tolerancing. So let's just take a look at the meter effect on a circuit. So anytime you place a meter across a circuit to measure either voltage or current, the meter is going to have an effect on the circuit operation. Anytime you place a meter in the circuit, it's going to add resistance to that circuit because all meters have resistance, and when placing them in a circuit, it's adding resistance to that circuit and therefore making that circuit different. So again, all meters have resistance. Digital meters tend to have much higher resistance than volt-ohm meters, VOMs. Digital meters will typically have resistances in the range of 1 megaohm to 1 gigaohm. I've seen them as high as teraohms. So you should always check the manufacturer's specification sheets to see exactly what kind of input resistance your particular meter has, especially if you're monitoring or measuring in circuits where the meter will have the greatest effect on them. VOM resistance is typically specified in ohms per volt, and 20,000 ohms per volt, 20k ohm per volt, is probably one of the most common specifications for VOM input resistance. Now that will vary depending on whether you're measuring DC voltage or AC voltage. 20,000 ohm per volt is fairly typical for DC voltage. 5,000 ohms per volt is fairly typical for AC voltage. Also, something that you need to keep in mind is that the meter resistance, in other words, the resistance that's going to be added to the circuit when making a measurement, has the most effect when you're measuring in high resistive circuits. Resistance or circuits that have a very high resistance. So let's take a look at a circuit, at a very simple series circuit, where we're going to make a measurement in this circuit. So I've given you the schematic diagram here where we have R1 is equal to 110 kiloohms, and this right here is the tolerance of the resistor, which for this exercise we don't really need this. And R2 is 1 megaohm. And again, we don't really need this 5%. The voltage source is going to be 24 volts, and it's a battery, so this is going to be DC. So let's do some calculations on this circuit. Let's find out what the current is in this circuit. Well, I already know that VT is equal to 24 volts. So to find the current in a series circuit, it's going to be the total resistance of that circuit divided into the total voltage. So resistance in series add. So RT is going to equal to R1 plus R2 plus, so RT is going to equal to 510 kiloohms plus 1 megaohm, or RT is going to equal 1.51 megaohms. That's 1,510,000 ohms. So with this now I have the total resistance and I have the total voltage. Therefore I can find the total current. And I is equal to V over R. If you're from the old school, this will be E T over R. You may have heard voltage can be represented with an E instead of a V. But so, and I tend to go back and forth between the two, but for the most part, textbooks today reference it as V. So IT, or I total, is going to be 24 volts, which is our voltage total, divided by the total resistance, and in this case it's going to be 15.894 microamps. So now I have the total resistance, or the total current of the circuit. Let's calculate the voltage drops across the two resistors. So now that I know that the current, and again I'm going to just get rid of these 5%. Now that I know the current flow through this circuit is 15.894 microamps. So everywhere in this circuit I'm going to have 15.894 microamps flowing. So I've got this current flowing in this circuit. So that means that current's going to be flowing through this resistor, and the current's going to be flowing through this resistor. Since I know the resistance and I know the current, I can calculate the voltage drop. And when I get the two voltage drops, they better add up to the source voltage. So let's look at the voltage across R1 will equal R1 times the current through R1, which is total current. So 510 kiloohms times the current through that particular resistor is going to equal 8.106 volts. So if I put a voltmeter across this resistor, I should be measuring on this voltmeter 8.106 volts. Let's do it across R2. So if I place a voltmeter across R2, the voltage across R2 will be equal to the resistance of R2 times the current across R2, which is total current. So 1 mega ohms times 15.894 microamps will be 15.894 volts. So this voltmeter should read 15.894 volts. If I take these two voltages, 15.894 plus the 8.106, we'll see 6 plus, and I'm going to add these. 6 plus 4 is 10. 9 and 1 is 10. 9 and 1 is 10. 8 and 6 is 14, is 24 volts. So I know my calculations are correct because the two voltage drops add up to my supply voltage. So that's really the analysis of that simple series circuit. Now, the voltmeter that we place across R2. So I got this voltmeter that I placed there, and take notice I have a resistance equal to 20,000 ohms per volt. So this meter is going to be 20,000 ohms per volt, and because I'm going to be measuring, let me go back, 15.8 volts, I'm going to use the 50 volt scale of the meter. Since I'm on the 50 volt range and it's 20,000 ohms per volt, the input resistance to the meter will be 20,000 ohms times the 50 volts, which gives me an input resistance on the 50 volt range of 1 mega ohms. So when I'm putting this meter across R2, when I'm placing it, I'm actually placing a 1 mega ohm resistance across R2. This meter I could literally replace. I can replace this meter with a resistor that's 1 mega ohm. So let's look at the equivalent circuit. So this is the equivalent circuit, where this right here is the meter resistance, Rm. So I have Rm in parallel with R2. So these two resistors are in parallel with each other. Since I have two resistors in parallel, and again I don't care about this 5% for this exercise, my total resistance of this circuit changed. With two resistors in parallel, anytime you have two resistors in parallel, if they're the same value, to find the total resistance of this, all I really have to do is divide by 2. So if I take R2 in parallel, that's what this means, in parallel with our meter, 1 mega ohm divided by 2, I am now at 500 kilo ohms. So literally, this circuit can actually be redrawn as being just a 510K, which is R1, in series with a 510K, which is the parallel combination of R2, Rm. Well, you can see pretty easily that this changed my total current flow. So let's do some calculations on this. So Vt is still 24. Total resistance, though, is going to now be R1 plus the parallel value of R2 in parallel with R meter. So I'm using the product over sum method here. This is called the product over sum. And when I have two resistors in parallel, I can easily do product over sum. Doing the mathematics, it comes out that RT is going to equal 1.01 mega ohms. Now that I have RT, I can now calculate my new IT, which is going to be Vt divided by RT, 24 volts over 1.01 mega ohms, is 23.762 microamps. So now, in the same circuit, but with the meter on it, I have 23.762 microamps flowing in this circuit. That current's then going to divide up here and join up on this side and continue traveling. But just for the fact that my current changed, we're going to be able to tell you that this voltage is going to also change. So without the VOM, the total voltage is still 24 volts. The total resistance is 1.51 mega ohms. The total current is 15.89 microamps. With the VOM across it, I'm still 24 volts, but my total resistance is 1.01 mega ohms. But look at how my total current dropped. The total current is now 23.76 microamps. So what voltage will the VOM display? We can easily calculate that out. We have IT equals Vt over RT, which is giving me that current. And now with that current flowing in the circuit, I can calculate out how much the voltmeter is going to read. So the voltage across R1 is going to be R1 times total current, which is going to be 12.118 volts. So this is going to be 12.118 volts. Since I know the voltage drop across this parallel set, plus this 12.118 volts has to equal 24. To find it, all I have to do is take VT minus VR1, so 24 volts minus the 12, and I find out that the voltage drop across here is actually going to be 11.882 volts. So you can easily see that without the VOM, I should have been measuring 15.894 volts. But with the VOM, I'm measuring 11.882 volts. That's quite a difference in voltage measurement. The effect on this meter had a fairly large effect. This meter had an effect of almost 4 volts on what the circuit is actually supposed to be reading.